All right, hello everyone, and welcome to our fifth lesson in the Unit 4 AP Chemistry curriculum on stoichiometry. Today's objective is to explain changes in the amounts of reactants and products based on the balance reaction equation for a chemical process. Stoichiometry is the study of quantitative relationships in a chemical reaction, meaning how much reactant is needed and how much product can be formed. A balanced chemical equation gives us the smallest whole number ratio in which substances react. These coefficients represent moles, so they act as exact conversion factors between reactants and products. So in this example shown, it has 2 moles of hydrogen gas reacting with 1 mole of oxygen gas to produce 2 moles of water. So for example, if you were given 1 mole of hydrogen gas and you wanted to figure out how many moles of water you would make, well, you would use something called the mole ratio, and the mole ratio comes from the balanced chemical equation. So I'm trying to get rid of moles of hydrogen gas, so I know I need to put my 2 moles of hydrogen gas from the balanced chemical equation on the denominator so that these units cancel out. And that is equal to the moles of what I'm trying to get to, in this case, water. So for my balanced chemical equation, I have 2 moles of water, and that means for every 1 mole of hydrogen gas, I produce 1 mole of water. So this relationship here, this fraction, that is called our mole ratio, and that is taken directly from the balanced chemical equation. So this is a diagram that is great for studying purposes if you are perhaps stuck on a problem. It essentially gives you a map of where you need to start and where you need to go, and labeled on the arrows is what you need to use to convert from one box to the other. So if you want to pause and take a look at that, I think it could be valuable if you need it. Remember, all stoichiometric calculations use mole ratios based on balanced chemical equations. So your very first step is to make sure that you have a complete and balanced chemical equation every single time. After that, you need to identify what you were given to start your calculations. So for example, if you are given grams of a reactant, you then need to convert grams into moles. If you were given moles to begin with, then you can go ahead and plug in your mole ratio. So the mole ratio is the conversion factor you're using to go from one substance to another using the mole ratio from the balanced chemical equation. And then finally, if you need to convert beyond that to a different unit, you would go ahead and do that. And this slide is just a simplified way of showing you how I personally do stoichiometry with conversion factors. If you do it a different way, that is totally fine. I just like seeing all the units and I like to see them canceling out so I know I'm not missing something. If you like to do this with formulas, that is totally fine by me as long as you show your work and get the right answer. And you can see here, just to circle back to mole ratios, the mole ratio is when you have moles over moles, and that number is from the balanced chemical equation. If you are working with converting units, for example, this is always going to be equal to 1 mole, 1 mole, 1 mole, 1 mole. So like if you're ever using molar mass to get to moles, it's always going to be the molar mass is equal to 1 mole. If you are using Avogadro's number, it's always going to be equal to 1 mole. The only time in stoichiometry where you're not using 1 mole is when you have the mole to mole ratio, and that is what is highlighted in the yellow boxes, and those numbers are directly from the balanced chemical equation. All right, so let's do a practice problem. So this says using 2H2 plus O2 reacts to form 2H2O, what mass of water forms from 5 grams of oxygen gas when we know that H2 is our excess reactant? So essentially this is telling us that H2 is our excess, so we don't have to solve H2 because we know that whatever oxygen gas produces, that is going to be our theoretical yield, which is the actual amount that we can make. So whenever we're doing stoichiometry, I always tell my students, start with what you're given. So we are given 5 grams of oxygen gas, and then figure out where you need to go. We need to go to mass of water. So I know if I'm going from oxygen gas to water, I need to use a mole ratio to get to water. And before using my mole ratio, I need to be in moles. So my first step is to get out of grams and get into moles. And I know that 1 mole of oxygen gas is equal to the molar mass of the oxygen gas. Now, oxygen has a mass of 16, and there are 2 of them. So we know in 1 mole of oxygen gas, I have 32 grams of oxygen gas. So now you can plainly see that grams of oxygen gas are canceled out, and we are left with moles of oxygen gas. Now that I'm in moles, I can go from moles of oxygen gas to moles of water. Now this is the mole ratio. You see moles over moles. I am getting these numbers from my balanced chemical equation. We can see that we have a 1 in front of oxygen gas, and we have a 2 in front of water. Finally, I'm in water, but I need to get in mass. So I'm going to take my moles and convert it into mass. And I know in 1 mole of water, I have 18.015 grams of water. Apologies, it's actually 18.016. So now I'm going to go ahead and make sure all of my units cancel out before I put all of this into the calculator. So I already know my grams of oxygen gas cancel out, my moles of oxygen gas cancel out, my moles of water cancel out, and I'm left with grams of water, which is exactly what it asked for in the equation. So now I'm going to go ahead and solve. So 5 divided by 32 multiplied by 2 and multiplied by 18.016. That's going to give me 5.63 grams of water. And then I need to look at my sig figs. 5.00 is the number we were working with, and that is 3 sig figs. So this is the correct final answer. All right, so another part of stoichiometry is the limiting reactant, the excess reactant, and the theoretical yield. So the limiting reactant is exactly what it sounds like. It limits the extent of the reaction and therefore determines the amount of product that is formed. So the limiting reactant, when you are solving, is going to produce less product than the excess reactant. So a portion of all the other reactants remains after the reaction stops, and those leftovers are called our excess reactants. And then just remember, the theoretical yield is the amount of product produced by the limiting reactant. Because again, once that reactant runs out, we can't make any more. So it limits how much product can be made. So let's do a practice problem with that. We have N2 plus 3H2 reacts to form 2NH3. We mix 25 grams of nitrogen gas with 10 grams of hydrogen gas. Find the limiting reagent and the theoretical mass of NH3. So whenever we're doing a theoretical yield or limiting reactant question, we do the same steps. I like to do them simultaneously. If you like to do it a different way, that is totally fine. But again, I'm going to start with what I'm given. So I have 25 grams of N2 and I have 10 grams of H2. So first step with our finding the limiting reactant and theoretical yield is figuring out what we're solving into. In this case, it's nice because we only have one product. But if we have multiple products, just make sure there's not an extension where you have to solve for a specific product. If there is not, you can just select whichever one you choose. You're going to get the same answer. But in this specific case, it told us what to solve for. So if we did have two products, we would already know which one that we were solving into. So now let's get back to the problem. So first step to get to NH3 is we have to get our reactants into moles. So we know in 1 mole of N2, I have the molar mass of N2, which is 28.02 grams. And then in 1 mole of H2, I have the molar mass of H2, which is 2.016 grams. Now that I'm in moles of my reactants, I can go into moles of my product using the mole ratio. So I want to get rid of my reactants, and I want to go into the same product. In this case, there is only one product, so that makes it nice and easy. Now, if it was just asking you for the limiting reactant, you could stop here and get the number and then figure out whichever one produced the smaller number. However, because it's asking for theoretical yield, I'm just going to solve both of these to the mass so that I don't have to recalculate later on. So, mole ratio, 2 moles of NH3, 3 moles of H2, and 1 mole of N2. That's all from the balanced chemical equation. And then I'm going to go ahead and solve for mass. So in 1 mole of my NH3, I have the molar mass of NH3, which is 17.034. So starting off with our N2, I have 25 grams divided by 28.02 times 2 times 17.034, and that gives me 30.396 grams of NH3. Then doing my hydrogen, I have 10 divided by 2.016 times 2 divided by 3 times 17.034. That's going to give me 56.329 grams of NH3. So we can see our theoretical yield of NH3 is the smaller one, so it would be this number here, which means N2 is my limiting reactant. And then if it was asking, H2 would be our excess reactant. All right, now let's talk about gas stoichiometry. So if your chemical reaction is at a single temperature and pressure, the gas volumes are going to be proportional to the mole ratios. So you can use the volumes the same way you would converting with moles. So for example, if we have this N2 plus 3H2 react to form 2NH3, if we were solving, and let's say we had 6 liters of N2 and you wanted to find out how many liters of NH3 you would make, you can use the balanced chemical equation just like you would for the mole ratio as a volume ratio. So we know we have a coefficient of 1 for N2, so 1 volume of N2 makes 2 volumes of NH3. So we know we would create 12 liters of NH3. because our volumes cancel out, our N2s cancel out, we're left with liters of NH3. So this is a very simple example, but that's only accurate if the temperature and the pressure are the same. That's very important. If that is not the case, then you are using the ideal gas law, but you are just rearranging it to solve for N, which is moles. So it would be N equals PV divided by RT, and then you just want to make sure you use the correct gas constant, which is on your formula sheet. So let's do an example for that. If 4 grams of hydrogen peroxide is placed within a sealed 250 milliliter container at 500 Kelvin, what is the pressure of the oxygen gas produced in atmospheres? So we are trying to solve for the pressure of oxygen gas. So we are looking for PO2. Now we are given grams of hydrogen peroxide, and we are also given volume of the container, 250 milliliters, and temperature at 500 Kelvin. So I'm seeing all of these components, and I hope that it's leading you to the fact that we are most likely solving using the ideal gas law. So if I'm solving for pressure, I know I'm going to have nRT over V. But if I'm solving for pressure of oxygen gas, I need to make sure my moles is also of oxygen gas. And right now I'm given 4 grams of H2O2. So in order to solve for my pressure using the ideal gas law, I first need to find moles of oxygen gas. So in order to get to oxygen gas, I first need to get this into moles. So in 1 mole of H2O2, I know that's going to be equal to the molar mass, which is going to be 34.016 grams. Now, using the balanced chemical equation, I can get rid of my moles of H2O2 and go to moles of oxygen, which is what I'm trying to get to. So this is my N now. So now I have moles of O2. I just need to solve. So 4 divided by 34.016 times 0.5 or divided by 2. So that's going to give us 0.0588 moles of O2. And now I'm going to plug that into the ideal gas law. So again, I'm solving for pressure. I now have my moles of oxygen gas, 0.058796. Just going to go a little bit more to keep units right. Since I want atmospheres, I want to use my gas constant that also has atmospheres, which is the 0.08206 gas constant. So that's going to be 0.08206. My temperature is already in Kelvin, so I'm going to leave that be. And then I am dividing by volume, which must be in liters. So that's going to be 0.25 liters. And I know that because I was given 250 milliliters. In order to get to liters, I know in 1 liter I have 1,000 milliliters. It's going to give me 0.25 liters. So now on my calculator, I do our moles times 0.08206 times 500 divided by 0.25. That is going to give me a pressure of 9.6496 atmospheres. And then I need to make sure my sig figs are correct. Technically, my Kelvin was in 1 sig fig, so I should be answering in 1 sig fig. So that's going to round up to 10 atmospheres of pressure. All right, and then finally, let's do a little solution stoichiometry problem. So whenever you have to do solution stoichiometry, most likely you are using molarity. Remember, molarity is moles over liters. So if you're trying to find moles, you are going to do moles equals concentration times volume in liters. So this one says, what volume of a 0.5 molar sodium sulfate will react with 275 milliliters of 0.25 molar barium chloride to completely precipitate all Ba2 plus in the solution? So it might help to think of molarity as moles per liter. So when we're doing this stoichiometry, we can cancel out our units. So I know what I'm starting with, the information I have in order to convert is this 275 milliliters of barium chloride, and then I need to get into volume of sodium sulfate. So it's kind of like a mass to mass stoichiometry problem, but now we're just doing volume to volume, and then we're using the concentration to convert from volume to moles, if that makes sense. So before we start all of that, we need to make sure we have a correct balanced chemical equation. So first we know our two reactants are sodium sulfate and barium chloride. So sodium has a +1 charge. Sulfate is SO4 2 minus. So I'm going to need 2 sodium. So it's going to be Na2SO4. And that's molarity concentration, which means it is dissolved in water. Then we have barium chloride. Barium is a +2 ion. Chlorine is a -1. So that's going to be BaCl2. Again, solution be aqueous or aqueous, whatever you want to say. Now we need to make our products. So this sodium is now going to pair with the chlorine. That's NaCl. You should know already that NaCl dissolves in water, but if you didn't, it is part of the AP chemistry rules because it has sodium in it. And then we have our barium pairing with our sulfate. Barium is +2, sulfate is -2, so it's just one of each. And we already know that our precipitate is the one with barium in it, so it's going to be our solid. All right, so now we need to balance this chemical equation, and by putting a 2 in front of NaCl, everything is balanced. How wonderful is that? So now let's go ahead and start all of our converting. So I know when I'm dealing with concentration, it's always in liters. So I'm going to first convert my 275 milliliters to liters by dividing by 1,000. So that means I'm going to have 0.275 liters of BaCl2. And I'm trying to get to liters of Na2SO4, which is my other reactant. So first step is to get to moles, and I am using my concentration because concentration, or capital M, equals moles over liters, right? So if I want to get to moles, I know I have 0.25 moles per 1 liter. So now that I'm in moles of BaCl2, I need to get to moles of Na2SO4. Those are both a coefficient of 1 from the balanced chemical equation. So that's going to be easy 1-to-1 mole ratio. And now I can go ahead and use my concentration of 0.5 sodium sulfate to get back to liters. So I know it's 0.5 moles per 1 liter. So I'm going to put that on the bottom, 0.5 moles per 1 liter. And that's going to leave me with volume of sodium sulfate. And now I just need to solve. So I have my 0.275 times 0.25, 1-to-1 ratio, and then divide by 0.5. That is going to give me 0.1375 liters of Na2SO4, which is not my final answer because that's not the correct number of sig figs. All three of the numbers given to us is 3 sig figs, so our final answer needs to be in 3 sig figs. So final answer would be 0.138 liters of Na2SO4. All right, and this is just a list of things to read through before taking a test or doing practice problems, just common mistakes on the AP Chemistry exam. All right, I hope that helps, and I hope you have a great day. Bye.